SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 19. We were talking about the various situations where there were the frequency distributions as normal curves for a process, and we were trying to meet the specification lines, particularly the upper specification limit and the lower specification limit with respect to the process mean and the spread. So there were three cases which evolved. Case 1 was when the process 6 sigma, which is the process spread, is appreciably less than the difference between the specification limits. You can see here that the amount of 6 sigma which is the spread is much lower in comparison to the difference between the USLX and the LSLX as recorded here. So the frequency curves A, B, C, D and E indicate various positions in which the process can be centered. For example, this process D would have a mean very close to the upper specification, while process E would have a mean very close to the lower specification, etc. So with any of the positions A, B and C, practically all the products manufactured will meet the specification as long as the process stays in control, because you can see that all these three are within the specification lines, and in fact anything outside this distribution C would just about cross the LSLX, so we would not really consider them in our process. So in general, when conditions A, B and C come, represent the ideal manufacturing situation. When the control chart shows that one of these control charts exists, many different possible actions may be considered depending on the relative economy. For example, it may be considered economically advisable to permit X to go out of control if it does not go too far, because obviously if you look at the way that, let us say, these are centered, the means are quite far away from the upper specification limit, or as a matter of fact the lower specification limits, and even a little bit of run out should be allowed. So the distributions may be allowed to move between positions, in fact B and C, if we are talking about the process mean and the spread of the process A. So this just to probably avoid the cost of the frequent machine setup and of delays due to hunting of assignable causes of variation that will not be responsible for unsatisfactory product, or where acceptance has been based on 100% inspection, it may be economical to substitute acceptance based on control charts. Okay. So that is really how the process spread and mean centered about the upper and lower specifications limit would actually indicate different levels and degrees of control which may be needed on the process. So now if we consider the, let us say, the position D or the position E, these are really serious situations where the mean is quite close to the upper specification limit in this particular case, as you can see, and towards the lower specification limit in this particular case, as you can see, and the spread also is in such a manner that there is a possibility that the process may just run out of control because of the mean and the spread. So these are really unacceptable processes. Okay. So you will have to do something so that you can either center the mean more towards the center of the upper and lower specification limit, so that the spread and the mean altogether comes within this domain. So there would be definitely a tightening of the process or a process control needed in cases D and E. So that is what you can say when you compare specifications to the actual distributions. There is another case which is a little more serious, when the process 6 sigma equals to the difference between the specification limits. So now you can see exactly, like let us say the A is a process which is the mean is centered about the central specification, and obviously there is going to be USL LX and LSLX as the upper and the lower bounds of the specification. So the mean and the specification mean are almost centric to each other. Okay. So even a little bit of deviation, for example you can see here B and C are deviated slightly from the position A, they are not allowed, because the moment that happens process goes out of control, and so you will have to do everything possible to bring the B, the mean at B or the mean at C close to the mean at A. Okay. So you have to somehow move these means together so the process still is in control. So this is how you read, based on the upper and lower specification limits, the various control aspects of the chart. So another possibility could be in this case to sort of probably revise the tolerance and see if it works out for this particular process, because obviously it is a very tight situation where the process mean and spread are just about good enough to be accommodated within the upper and lower, and a little bit of decontrol also leads to outruns and many rejects, as you can see here. So obviously either you probably change the the process control by making this little bit tighter, so that you can have the spread lesser, or alternately you can change or think of changing the specifications if need, if there is a lot of factor of safety which has been put in the original design, so that still the process can be within control. So there are various ways to do or execute this. There is another case which I would like to discuss, which talks about when the process 6 sigma is actually less than the difference between the specifications. So irrespective of whether it is center or not, there is going to be a loss in terms of rejects of the products that the process produces. So even if you can center around, the mean does not work out. So now this needs really a process change. Okay. For example, you can go from, let us say when we are talking about a diameter of a shaft, we can go from a manual system to an automatic system, or maybe a CNC controlled system, to sort of reduce this variability sigma, so that the mu plus minus 3 sigma would always fall between the USL and the LSL. So that is what exactly has to be done. If it is not possible and it is already the process is at the limit of its capability, then obviously we will have to think of changing the specifications in this case, if you want the process to be producing parts which are acceptable. Otherwise the process just is not feasible in this particular manner. So these are how you interpret the various cases where the different means and standard deviations put together are sort of rhyming with respect to the upper and lower specification limits. So I would just like to show a little different situation here, where the possible relationships of a process in control to a single specification is identified by 3 different cases: case 1, case 2 and case 3. In this particular case, for example case 1, as you may see, there are different processes A, B and C with a certain spread and a mean, and although the means are all differently shifted and the spreads are all different, the lower specifications or the lower acceptable limits are more or less same for all the 3 processes. So in case 1, the low value of distribution mu minus 3 sigma is appreciably above the LSL, the lower specification limit for X, which is actually a good thing, because everything is that is produced is acceptable in this case. And case 2 is a case where all of them are lying on the LSLX. That means a little bit of deviation in terms of maybe the change of the mean would in the downward direction would make a part of the process unacceptable. And the case 3 is even a little bit different, it is like quite serious, that if you look at all these 3 A, B and C distributions, the processes indicate a greater amount of reject when the spread is a smaller, or maybe a little bit lesser amount of reject if it is larger, and the least amount of reject if it is even the largest. So in a way, if the sigma alters and the cases where all the processes are sort of rhyming with the lower specification limits, it is always wise to have a greater sigma. Let us say this is sigma 1, this is sigma 2, this is sigma 3. So obviously sigma 3 is greater than sigma 2 is greater than sigma 1. So you can always think of having a greater sigma, okay, so that the mean can be accordingly shifted, particularly in cases where the lower specification limits are sort of all similar to each other, or the lower percentage of rejects are same to each other. So in this particular case, as you can see, greater is the sigma or greater is the process spread, the better it is. Okay. So such cases do exist, where there is always a alignment of the lower side of the limit of rejects and of the particular process, and the moment that goes or starts going outside the lower specification limit, it is always wise to have a wider spread than a smaller spread, as can be seen in this particular example. So such practical decisions have to be arrived at sometimes by a process control engineer or a quality control engineer, and let us just detail all these possible relationships of a process in control to a single specification, particularly the LSL as you were seeing there. So the first situation is one in which there is a margin of safety, obviously second is a one where the specification is just barely met as long as the process stays in control, and the third is one in which some non-conforming products are produced unless there is a fundamental change in the process spread or increase in the process average. So all three distributions A, B and C have the same lower value, however the distribution B with a greater dispersion must have a greater process average than A for the low points to be at the same level. Similarly, distribution C should have a greater process average than B, as I talked about before. So it is evident that the greater the distribution, the higher the average must be for the entire distribution to fall above the lower specification limits. And the relationship between average and cost is vital in many instances. For example, in the filling of containers, the reduction in dispersion may reduce cost by reducing the average overfill. On the other hand, the less the dispersion, the more important it is that the process average goes out of control, and this is illustrated by comparing distributions A and C in case A, B and C in case 3. Both process averages have shifted an equal amount below their position, however the proportion of bad products are indicated by the area of the distribution below the specification limit is greater in A than in C. So as I told you that it is advantageous in that particular case to have a greater spread of the process at a higher average or a mean rather than a lower average mean and a lesser spread of the process. So that is how we sort of indicate the various relationships in this kind of a single specification meeting situation. So we now demonstrate some of the uses on the control charts by a purchaser to help suppliers improve their processes. There is a case which is given here. A manufacturer of electronic devices had trouble with cracking of certain small cross section ceramic insulators used in the device. So the cracking generally took place after manufacturing operations were nearly completed, and so in a way they made it impossible to salvage the unit. So you will have to just throw the unit once the crack has developed. So hence the cost resulting from each cracked insulator during manufacturing operations suggested that the others might likely crack under service conditions, and so in an effort to improve the situation, all incoming insulators of this type were given 100% inspection. Now this 100% inspection failed to decrease the percentage defective units. So a simple testing was constructed to measure the actual strength and flexure by testing insulators to destruction. From each incoming lot of insulators, 25 were tested. As the insulators came from two suppliers, control charts of X bar and R were plotted from both suppliers, and they were separately maintained for a long amount of time. The test showed that both suppliers had approximately the same percentage defect, but the explanations for the defectives were the following. So supplier A had a higher average strength but complete lack of anything resembling statistical control. B on the other hand had excellent statistical control, but at a level such that an appreciable part of frequency distribution was below the required minimum strength. So this diagnosis of this situation was brought to the attention of both the suppliers, and they could encourage to sort of exchange information about production methods, and finally the product control could be achieved. So it shows how control charts were used for checking the defects which were actually alternating for different kind of defects between the two manufacturers, and they were simply exchanged on each other so that they could have a better control of both the processes and learn from each other's strong points. Okay. So I think I had earlier described the milling of a slot in an aircraft terminal block. I am going to just maybe go through a few more issues in this particular terminal block. So what are the decisions which are preparatory to the control chart? Why the terminal block example was chosen in the particular industry? So there are high percentage rejections for many of the parts made in the machine shop of an aircraft company, and this indicated the need for examination of the reason for trouble. And as most of the rejections were for failure to meet dimensional tolerances, it was decided to try to find out the causes of trouble by use of the X bar and R charts. And these charts, which of course required the measurements of dimensions, were to be used only for those dimensions where it was causing numerous amount of rejections. So particularly the milling slot width in this particular case was taken as a dimension. So among the many dimensions, the one selected for the control charts were those having high cost of spoilage and rework. So we very judiciously the company chose that particular dimension which creates a lot of low value added to the system in terms of rework or spoilage or rejection, or even like not being able to fit on the electrical panel properly, so on and so forth. And those on which rejections were responsible for delays in assembly operations were also considered. And so one critical dimension was found or isolated to be of very important nature, and that was the width of a slot on the duralumin forging used as a terminal block at the end of the rear tail of an airplane. So the final matching of the slot width was a milling operation, and the width of the slot was specified to be 0.8750 mean. This is inches, so it is basically inches mean, and then the specification limits said that it has to be within plus 0.0050 inches and minus of 0.000 inches. So that is about the way that this example was envisioned. The design engineers had specified this dimension with an unilateral tolerance because of the fit requirements of the terminal block, and it was essential that the slot width be at least 0.8750 inches, and desirable that is very close to this value. And so now the question arises that once this dimension has been sort of isolated and the specifications being laid out, the next step, which is the control chart plotting, comes into picture. So I am going to close this module in the interest of time, but in the next module we will start as to how this chart was plotted and how you can have various information from this chart which leads to some learning experiences. Thank you.